In this video, we're going to take a closer look at binding energy and how it relates to stability and energy wells. You've seen this picture before. It's the binding energy per nucleon. And what it tells us is how much binding energy each nucleon has when it's inside of a different nucleus. For example, each nucleon inside of hydrogen has about 1 megaelectronvolt of binding energy. Each nucleon inside of iron has more, about 9 megaelectronvolts. But this is confusing. You might be wondering, what is binding energy? Is it the energy inside a nucleus? The answer is no. Binding energy isn't the energy that a nucleus has. In fact, it's the opposite. It's the energy that a nucleus doesn't have anymore. To understand this, let's remember what happens when a nucleus forms. We have 3 nucleons, and let's just say that the energy they have right now is 0 megaelectronvolts each. We bring them together, they form a nucleus, they lose some energy and mass as a result. Each nucleon here is losing 4 megaelectronvolts of energy. So the energy is no longer 0 because each has lost 4. So each nucleon then has gone from 0 down to -4. That's the new value of energy per nucleon. Okay then, this is hard to represent. We can't really see the energy that's being lost in this picture. So instead, we use energy wells, or as you'll later see, they're called potential wells. So here's the picture. When the nucleons are free and unbound, they're at the top of the well, where they have 0 energy. When the nucleus forms, they fall down into the well, and they lose 4 megaelectronvolts each. That energy is given off as electromagnetic radiation, and it carries away some of their mass. So this picture clearly shows us that the nucleons have gone down to a lower energy level, or an energy state. They started out at the top, where the energy amount was 0, and now they are down at -4. That's a lower energy state than where they started. Okay, so what do we know so far? A nucleon has more energy when it's outside of a nucleus, and it has less energy when it's inside a nucleus. But we don't care about just a single well or just a single nucleus. We want to compare lots of nuclei, like hydrogen, down here, helium, iron, plutonium, radium. We are interested in seeing the difference between lots of different wells or nuclei. With some nuclei, or wells, nucleons have -3 megaelectronvolts of energy. With other nuclei, each nucleon has -4 megaelectronvolts of energy. And because -4 is smaller or lower than -3, we make this well deeper, so that these nucleons are at a lower energy level or a lower energy value, because -4 is smaller than -3, so these are lower. Other nuclei get even lower, down to -7. So the nucleons inside those nuclei, each nucleon would have -7 MeV of energy. And yet, even though all of these nucleons have negative energy, somehow, for some reason, we say that the binding energy per nucleon is +3, +4, +7, And that's really misleading, because what we really mean all along is that these nucleons each have -3 MeV, and these each have -4 MeV of energy, and these each have -7. So it's really misleading that we use positive values for binding energy. And ask ourselves now, is binding energy the energy in a nucleus? And look at this picture and try to figure out what you think the answer is. Does this nucleus have +3 MeV? No! Binding energy is exactly the opposite. Binding energy is the energy that the nucleons don't have anymore. In other words, it's the energy that's lost when a nucleus forms. We started out at 0 and we lost 3, winding up at -3. The higher the binding energy per nucleon, here's 4, here's 7, the higher the value, the more energy we lose, and the lower our energy state. So the last thing is to look at all of the wells together and think about stability. As we go down into deeper wells and deeper wells and deeper wells, we are getting to lower energy values. We're going from 0 to -4 to -7, which is smaller, to -9, which is even lower. So we are reaching lower and lower energy values or energy states. But the binding energy, for this well, the binding energy would be +4. And here, the binding energy per nucleon would be +7. And here, the binding energy per nucleon would be +9. So the binding energy per nucleon increases as we go down. Here's the thing about wells. If you have a nucleon right here, it's pretty easy to get it back out of the well. Or in other words, it's pretty easy to break it off of the nucleus. All you have to do is give it 4 MeV and it hops out. If we have a nucleus where the nucleons are down here in a lower well, this is a little harder to break the nucleon free or to hop it out of the well. To get this out of the well, you would have to give it 7 MeV, and then it would be back up at 0. And if we're all the way at the bottom, that's when it's the hardest to break the nucleon free from the nucleus. We have to give it a full 9 megaelectronvolts to pop it back out and get it to 0. So that it takes more energy to get nucleons out of deeper wells. And because of that fact, the deeper wells are more stable. Or in other words, the higher the binding energy per nucleon, the more stable the nucleus.